I'm Kevin Weber, and on today's episode of The Bring Up, we're nuking a camera with a proton beam. Oh, and continuing our discussion about space!
So good to have you here, finally.
I heard you want to talk about technology. You don't have to twist my arm too hard on that topic.
Cheers.
Cheers. Are you looking for secrets?
Bring up.
Bridget. She's dead. You may not like it, but this is what peak performance looks like.
Hi everyone, and welcome to The Bring Up. In our last episode, we discussed how AMD's engineers harden our silicon chips for the harsh heating and freezing they experience in outer space. But that's only half the story. There's another force at play: radiation. And for that, we'll have to go on a little trip to Davis, California. So let's throw it to Cabin in the Field. So we're here at Crocker Nuclear Laboratory at the UC Davis campus, where teams of experienced engineers do the unthinkable: be at a radiation testing facility on a daily basis. I certainly didn't intend to wander the facility on my own, so I had our principal engineer, Pierre Maillard, give me the tour. All right, Pierre, I'll be honest with you. I have seen enough docuseries about the Chernobyl incident to have developed a deep-seated and inexorable phobia of radiation. So what can you tell me about being in this very scary laboratory that might make me feel a little bit better?
All right, well, let's get out of the facility first, right? So radiation is really part of our everyday life, and we usually refer to it as background radiation. We have some radiation that we're very familiar with. It's UV rays. They are very crucial to, for example, help us build vitamin D, but also, in excess, they can be detrimental to our health. Think about our chip at AMD being a bit the same. Chips have some sensitivity to radiation, not from UVs, for more what we call galactic cosmic rays. And so without the proper mitigation in place, we basically will have sensitivity issues.
So we've got a chip in space, a little computer. There's a bevy of high energy particles that are all zipping around. And what happens electrically at like a circuit level that actually causes damage or upsets a circuit?
So when a charged particle goes through a silicon, it induces some type of upsets. It could be a bit flip, it could be a high current state, it could be a loss of functionality. Those are usually referred as single event effects.
Pierre mentioned SEEs, or single event effects, and these are one of the most important kinds of issues caused by radiation interacting with an integrated circuit. Now, in a piece of silicon, there are often billions of transistors, and a transistor, in the simplest possible terms, is an electronic switch with two possible states, on or off. Now, in normal operation, a computer controls every aspect of how and when its transistors turn on or off. But when radiation comes into play, any transistor could be hit with a high-energy space particle and suddenly flip its state, turning it on to an off, or vice versa. This can lead to a range of results, from no big deal to correctable to really very bad. So let's start with the best-case scenario. A lot of times when a transistor is flipped by a high-energy particle, the effect is transient, meaning it only flips for a short period of time and then reverts to its original state. If you're not actively reading that bit in the moment that it's flipped, then it's no harm, no foul, and the system continues as expected. This is an SEU, or single event upset, that does not affect the operation of the system. Now we'll move on to correctable bit flips. Let's take the previous example where a memory bit was flipped, but this time we happen to read it during its transient state, or perhaps it wasn't a transient error and the bit flipped and stayed flipped, which is also possible. Now we have an issue because we're trying to operate with corrupted memory. Thankfully, engineers can design in error correction, which means the memory circuit itself can detect if a bit has been flipped and correct it. Or at the very least, send up a flag to the system to say, nothing is valued here. This is not a place of honor. And finally, we have really very bad territory. Some transistors are pretty important, and pretty bad things happen if they get flipped. Imagine, for example, the flipped transistor is in charge of rebooting the device, like a reset button on a PC, causing a full system reboot of a spacecraft as it's on its descent to Mars at 12,000 miles an hour. This is an SEU that evolves into its meaner older brother, the SEFI, or Single Event Functional Interrupt. This means that a bit flip occurred, was not corrected for, and caused a function to fail. Which to me, sounds pretty scary.
It's only scary, if we don't understand the concept, right? But for example, at AMD, we do spend a lot of time understanding the impact of those radiation on the process, on the silicon that we use ourselves, so we can build the proper solution. And so I would say, in a way, it's less scary, right? Once we've gone through, a few iterations at facility like here, Crocker, to do proton test, and we understand the impact that those radiation have on our silicon, then we can build a proper solution.
Can you explain an example of one of the kinds of mitigations you would develop or design that might prevent one of those single event upsets or one of those the failures?
Imagine having our part in a satellite or in payload in space. The last thing you want is having to reprogram that part. Let's take a very simple example, memories. To avoid uncorrectable event in the memory, you need to have some type of protection. And you mentioned it earlier, error correction circuitry, ECC. The problem with some of the solution like ECC is that as your charge goes, it's not really just a single event upset in the sense that we think about it as a single memory. It's an array of memory. And so the charge will spread through the memories and it will flip many of them. And so what we will do is we will do something called memory interleaving. Based on the information we get from the technology, the process, we'll be interleaving the memory to allow enough spacing between each bits in the word so that the ECC code can come and correct.
So we know the kinds of problems that can occur. We know how you mitigate them in design, but why are we here at this test facility today?
So we're here because what we're trying to do is demonstrate that our solution, the one we architected and taped out in our products, is actually working. And so what we're going to do is we're going to take a chip and put it in the path of a proton beam and measure the amount of single event upset we will be observing. Primarily, we're looking today at single event upset and functional interrupts.
Now, there's something magical about engineers. No matter how many degrees they've earned or papers they've published, there is forever present the cat-like curiosity and thirst for knowledge that powers their urge for discovery. And occasionally, that beautiful whimsy can be exploited to do cool shit on camera. We had a team of professionals trained in firing radiation at electronic parts, so naturally I asked them if we could put a camera in the path of the beam, and much to my surprise, they all said, yes, that sounds really neat. So I had Pierre help me set up a camera directly in the path of the test beam, and after skedaddling behind a 4,000-pound water-filled concrete door, we fired up the beam at a total current of 100 picoamps. Not great, not terrible. Here's a POV of the event in action. Immediately you can see a shower of sparkles on the camera sensor, including both a good amount of luminance and color noise. Notice some of the larger spots where multiple pixels are affected simultaneously, and others where the spots are long and oblique, where it seems the particles have bounced off and hit the sensor at an odd angle. The camera still appears to be functioning normally, but what we didn't realize until reviewing the footage is the audio cuts out completely about 30 seconds into the test, which means we got our first single event functional interrupt. I wasn't using or monitoring the audio, so the audio failing was a functional interrupt that didn't meaningfully affect the performance of the part. If this were a Mars rover, it might be the equivalent of an extra sensor going offline or a redundant system being affected, something that is not going to critically affect the mission. But that wasn't enough for me. I didn't fly out to California for a little audio dropout. I wanted total radiation-induced failure. So we upped the amperage by 10x all the way up to 1 nanoamp. And that poor camera didn't stand a chance. After a few seconds, the feed froze completely. Definitely a serious functional interrupt for a camera system, and a fun little memento. So what did we learn from this test? When we rebooted the camera, it continued to work just fine. It was so radioactive we couldn't remove it from the facility, but other than that, it was relatively unscathed. All we can safely surmise is that this camera won't stand up to a 15-year mission in outer space without rebooting. And honestly, that's fine, right? Being blasted with proton radiation probably wasn't in the design specs for this part, and rightfully so. The design and engineering costs necessary to radiation harden a part that nobody outside of me in particular would ever experience wouldn't be valuable, and would raise the costs of the product unnecessarily. Let's go back to Pierre and ask what it's like to design something that does have those strict requirements.
We're gonna prepare our experiment, come to the beam it, ensure that what we're seeing, we can reproduce it. We have error bar associated to it that are acceptable. And once the product is taped out, we still come back at the facility again. And that's the part where we want to, again, demonstrate, validate that our solution works, right? So by the time the part is in space, it's more like a lot of joy and excitement to imagine that us, AMD, is contributing to humankind in a very positive way.
So at AMD and with technology in general, innovation is required. We are constantly advancing, constantly creating new technologies. What do you have to do to also innovate or also kind of move forward with this technology?
Innovation is a crucial part of building the next generation of radiation effect solution. The amount of memory, of logic, of registers in our device is increasing, right? And as we're doing, such as the targets for radiation. So then you have key parameters such as power, performance, area that comes in place. We want to be able, for example, to enable AI in space, AI machine learning or classification or detection. Those are applications that require some very significant amount of performance. We have to all constantly think about ways to semi-seamlessly put in the radiation solution in place so we can achieve performance while bringing up those silicon into space, right? So radiation tolerance with performance, with power, with area. So really the idea is innovate to optimize those different parameters so we can have the next generation of product.
Well, Pierre, thank you so much for joining us. And now more than anything, I would like to leave this place and never come back.
All right, sounds good.
Part of the reason I love AMD is its culture of engineers. The effort and expertise necessary to create a part that starts here on Earth and spends the rest of its life on another planet seems impossible. But by taking a problem, dissecting it into its constituent parts, and solving each one until the problem is fully understood, that's how you achieve the impossible. Well, that's it, folks. We got to learn a little bit about why space is cool to look at but bad to be in, how we guard our most specialist parts for their journey to other planets, and I didn't even have to add myself to Wikipedia's list of nuclear radiation accidents and incidents, which I read 3 times before visiting that facility. A million thanks to Pierre and Crocker Nuclear Laboratory for all their help and professionalism, and most of all, for making me feel safe. Thanks to their strict safety standards, even after 2 days of being in their lab, my dosimeter read a cool 0.0, my favorite amount of radiation to be exposed to. As always, please be sure to like and subscribe, and expose that bell icon to so much cosmic radiation that it latches, and you never miss a future episode. We'll see you next time.